Okay, so continuing on, I'm going to make a separate video that deals with naming bicyclic compounds because there's some questions in the homework that refers to that. So I will make that in a separate video and I will post that as well. I'm going to go ahead and move on with the remainder of the chapter for chapter 4. And so kind of a next little tie off or like spin off from nomenclature is how to know whether or not you're dealing with constitutional isomers or not, right? So just as a reminder, what a constitutional isomer was is that constitutional isomers are compounds that have the same molecular formula. So we have the same molecular formula, but they differ in the connectivity of atoms. Connectivity of atoms, right? And so I'm spelling well today, so that's a good sign. So as an example of that, right, we had, when we talked about Lewis structures and the very beginning of the course, we talked about constitutional isomers, right? And drawing various constitutional isomers. So we have moved away from Lewis structures and we've gone more towards drawing these bond line structures. So let's say that you had a question where it was like, oh, draw all the constitutional isomers of hexane. Okay, so hexane has a molecular formula of C6H14. And if you were going to draw just a straight chain hexane, you would essentially just draw a bond line structure with 6 carbons, right? So we could go through and say we've got 1, 2, 3, 4, 5, 6. So one of the first constitutional isomers of hexane here would be this guy, right? So this is hexane as is, okay? Okay, so with that, like let's say, okay, well that's one constitutional isomer of hexane. What if we wanted to draw another constitutional isomer? And it wouldn't be hexane at that point, obviously it would be named something different, but of this C6H14 molecule, right? And so one thing that we could do is that we could take, let's say this methyl group off of the end here, and we can move it and put it on one of the interior carbons, right? So another way that we could draw this C6H14, we could draw a pentane chain with, again, a methyl group moved towards the interior. Okay, so again, this is another constitutional isomer of this C6H14. This is no longer hexane. This is going to be named something different. Okay, so again, we're trying to find all of the constitutional isomers, let's say. So we could do the exact same thing where we, again, redraw that pentane, and then we, let's say, move that methyl group to the carbon in the middle. All right, so again, another constitutional isomer, right? Now, if I tried to continue to do that, so if I redraw pentane and I put this guy on the next carbon over, I just want to note that this guy and this guy are the same molecule, right? So anytime you can, let's say, pick up a molecule and then overlay it onto another molecule and get the exact same thing, that tells you that this is the same molecule. So I could pick this guy up, I could rotate it and overlay it on the top molecule, and they overlay exactly, so that's the same molecule. So this guy would not be a constitutional isomer of this thing. Okay, we've already drawn that essentially. Okay, so another thing that we could do is we could come back and say, okay, well, I'm going to take this methyl group, and I'm also going to take another methyl group. So let's say we also take another one off. And so instead of drawing a pentane, let's say that I instead draw a butane, 1, 2, 3, 4. And now let's say, okay, I'm going to put one methyl group here and one methyl group here. Okay, so again, this is still our C6H14. We've got 1, 2, 3, 4, 5, 6 carbons. If we counted the hydrogens, we'd find there's 14 hydrogens. Okay, so I can do that again, right? So I could, let's say, draw another butane, and let's say I put both of those methyls off of one carbon. Again, that's another constitutional isomer. Let's say I, again, draw another butane, and then instead of having 2 methyl groups, let's say that I combine those 2 carbons and make an ethyl group. And I draw that ethyl group off of this guy, okay? So now, you would think, drawing it this way, that we have drawn, again, another new constitutional isomer. But in reality, this is actually just a repeat of this guy, right? And so the way that we draw these can change. It can vary, right? Because what we'll find is that all sigma bonds, all single bonds can rotate. But how would you know that? All right, they don't look the same. Like the one that we drew up here, where we had drawn the pentane with another methyl group, you can kind of see that these guys actually look the same, even though we've drawn them slightly differently. But here, this guy and this guy, which are the same compounds, they don't look very similar, right? So sometimes you will be asked whether or not something is the exact same compound or whether it is a constitutional isomer. And they will again be drawn in kind of drastically different ways so that you can't necessarily tell. So then the question is, well, how would you know? Okay, and so the answer to that comes in the form of nomenclature, right? If we named these compounds, so if we named this guy, we would name this is 5 carbons for our parent chain. So this is pentane. Again, if we numbered it, we have 1, 2, 3, 4, 5. So we have a substituent off of the 3 position. So this would be called 3-methyl pentane. If we named this compound, and it's the same compound, it's going to give you the same name, right? So if it's the same compound that you've already drawn, it's going to have the same name. If it has a different name, then it's a different compound, right? So different name is going to give you a different compound, a different constitutional isomer. So different constitutional isomer. If it has the same name, though, we're dealing with the same compound. And so if we had gone through and we had named this other guy, again, we're looking for the longest carbon chain for our parent. Here, the longest carbon chain would be 1, 2, 3, 4, 5. So again, this would be a pentane. So this is a pentane. If we had numbered it, we'd get 1, 2, 3. We have a methyl group again, branching off of that 3rd carbon, so this would be 3-methyl pentane. So if you go through and you're asked, hey, are these the same compounds, or are they different compounds, are they constitutional isomers? If you name them and they have the same name, then it's the same compound, they're not constitutional isomers. If you name them, on the other hand, and they have a different name, then they're different compounds, and they're constitutional isomers of one another, right? As long as, again, they have the same molecular formula. Okay, so with that, I want you guys to give this one a shot. So I have 2 compounds, right? 2 different molecules here. And I want to know, are these guys constitutional isomers? Are they different compounds? So again, this means that they are different compounds, but with the same molecular formula. Same mole form. Or do they actually represent the same exact compound, just repeated? Okay, so the idea behind this, you should go about naming both of these, right? If they have the same name, that should tell you something. If they have a different name, that should tell you something. So go ahead and pause this, give this one a shot, and then come back for the answer when you're done. Okay, so I'm going to go ahead and start by naming the compound on the left first. So if I go through this, I'm looking for the longest consecutive carbon chain for my parent. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. So the parent chain for this guy is 10, which is decane. I'm then going to look for my substituents. We've got 1. I did not want the pen. I wanted the highlighter. 1, 2, 3. And then we've got this guy. So all of these guys with the 1 carbon chain, these guys are all methyl groups. So we've got a methyl, and a methyl. And then the other guy had 1, 2, 3 carbons. So 3 is our propyl. Okay, so after parents, after substituents, we're going to number the chain. If I started out here, I wouldn't get to my first substituent until 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5, that's bad. Over here, though, if I started here, I'd have 1, 2, and my first substituent would come at the 3 position. So this is how we're going to number. We have 5, 6, 7, 8, 9, and then 10. And now we're ready to assemble the name. So for my substituents, I've got methyl and I've got propyl. Methyl comes first in the alphabet because of the M. There are 3 of them, so this is a trimethyl, and again I have to specify where they're at via our locants. So we've got a 3, a 4, a 5 trimethyl, and then we move to our propyl group. We've got a 6 propyl, and then we move into our parent decane. Okay, so that's the name of compound 1. Compound 2 does not look like compound 1, right? So it's not something that we could just say, oh, I can pick up. I can obviously see this is the same compound. So to answer this question, we have to determine its name. If we look for their parent chain here, the longest chain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, we have a decane. If we look for our substituents, we've got a methyl, we've got a methyl, a methyl, a methyl, and again we've got a propyl group. So we've got 3 methyls, another trimethyl, we've got a propyl. And now the question is, well, do all of these methyl groups lie at the same position, right? So again, if I started numbering over here, I'd have 1. I wouldn't get to my first substituent until the 5th position. If I start over here, though, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now, same exact thing. We've got a methyl versus a propyl. We're going to put the methyl first. It ends up being 3, 4, 5 trimethyl. Go figure. And then we've got the propyl at the 6th position, 6 propyl. And then we'll zoom out. And then we move into our parent decane. So the name is the same. And so that tells us that these guys are not constitutional isomers. Instead, they are the same compound. Same compound. Right. So, purpose of this. Hey, you're going to be given 2 molecules. They look different. You're not going to be able to say whether or not they are constitutional isomers or not. The way you're going to answer that question is you're going to name them. If they have the same name, it's the same compound. If they had different names, they would be different compounds, and therefore, as long as they had the same molecular formula, they would be constitutional isomers. Okay, so that is that. Okay, so keeping kind of on this conversation of these constitutional isomers, we have one little other topic we need to address before we move on, and that has to do with the stability of various isomers, right? So I've been mentioning this word stability quite a lot, but maybe I don't necessarily define what it means. So when I say something is stable, what I'm implying by that is that it is less reactive, and what that means in terms of energies or energetics is that things that are more stable, they're less reactive. That means that they lie at a lower potential energy state. So lower potential energy comparatively to things that are unstable, which means that they're more reactive, meaning that they lie at a higher potential energy. The higher the potential energy overall, the more reactive you're going to be, the less stable you are, okay? So if something is stable or more stable, it's less reactive. That means it lies at a lower potential energy. So kind of the question that we're asking at this point in terms of these constitutional isomers is who in like a gamut of constitutional isomers, who actually is more stable, right? Is there a difference, let's say, between something that is like more straight chain versus something that's more of a branched isomer? So an example of what I mean by that would come from constitutional isomers of C8, H18, right? So if we look at C8, 8 is octane, right? And there are a couple of different isomers that are going to constitutional isomers that are going to match the C8H18. So one way that we can draw this is our what we call a straight chain isomer, meaning that this is going to be the actual octane, right? If we named it, it would be octane, where essentially we don't have any branching, we don't have any substituents. All we have is our 1, 2, 3, 4, 5, 6, 7, 8. Really? That's not 1, 2, 3, 4, 5, 6, 7, 8. Darn it, Chelsea. Come on. No, gotta get back. Okay, so yeah, I drew it right originally. So again, this guy is the actual octane that we're talking about. And again, what we would call this is a straight chain isomer, meaning there's no branching. It is just a long carbon chain of 8 carbons together. Okay, so now let's say that we were comparing the stability of this isomer of C8H18 to something that was much more what we would call branched, right? So another isomer of C8H18 is this guy, right? And let me make sure and count carbons because obviously I'm a failure at that. We've got 1, 2, 3, 4, 5, 6, 7, 8. Again, if we counted hydrogens, we would find that there are 18 of them. So this is also an isomer of C8H18, but now this is not what we would call straight chain, right? Now we have a lot of branching. So this is a much more branched chain isomer, so a branched isomer. So again, the question here that we're asking is who is more stable, who is less reactive, who is at a lower potential energy state, or are these guys the exact same, right? So are they at the same energy, or is one of these a little bit more stable, a little bit less reactive? And so how would we answer that question, right? So we need to know something about the energetics of these guys. And so the way that we do that is by measuring heats of combustion, right? So anytime we deal with energies in terms of these isomers or these various compounds that we deal with, we're usually going to be measuring them by seeing the amount of energy they release in a combustion reaction, right? So for the straight chain octane, that reaction is taking our C8H18, right? And in a combustion reaction, all we do is we combine it with molecular oxygen, right? In the process of this reaction, what we're going to find is we're going to form CO2 and we're going to form water. And in this overall combustion reaction, we can measure the heat that is released by measuring the change in temperature of the reaction, right? We can use a calorimeter or however. And again, we usually convert that in terms of our energies to enthalpies, right? So this usually is called this heat of reaction. And that's really ugly the way I wrote that. So now the only thing that I haven't really included here in this reaction is balancing it, right? So if we balance this, we would have 8 CO2s, we would have 9 H2Os, and then if we balance everything, we would end up with 12 halves oxygen. Okay, so we take our straight chain octane, let's say we combust it, we combine it with molecular oxygen, we form our products, and we measure the heat that is released in that reaction. And for this guy, we end up measuring the heat here as a minus 5,470, and this ends up being in kilojoules per mole. So again, this is a very exothermic reaction. We've got a nice negative delta H, and it's fairly exothermic because that's a lot of energy released. Okay, so we can do that, right? We can do that with our straight chain octane. Let's say that we did the exact same thing with our branched octane or our branched C8H18 molecule, right? So now this guy we're going to look at in red. So again, if we take the molecular formula for it, it's going to be again our C8H18. We're going to take it, we're going to put it in our calorimeter, we're going to combine it with molecular oxygen. We're going to form again CO2, and we're going to form water. And if we balance this, we would get the exact same balanced chemical formula because they have the exact same molecular formula. So this would also be combined with 12 halves oxygen. We would make 8 CO2s, we'd make 9 H2Os, okay? We do it, we put it in our calorimeter, we burn it, right? We measure the heat that is released. You may think, well, it's probably going to be the same, or if it was the same, that would tell us something about these energy levels. But actually, we get a different enthalpy of reaction here, a different heat of combustion. We end up getting only 5,452 kilojoules per mole for this guy, our branched isomer. Okay, so now the energies here are different, and that should tell us something about the energy differences between our products and our reactants. Okay. So now, if we remember, with respect to delta H, anytime we have a delta, we're looking at the enthalpy difference between the products, right, and the enthalpy difference in our reactants, right? So anytime we measure a delta, it's always final minus initial. Final state is the products, the initial state is the reactants. Now, for both of those two reactions, we had the exact same products formed, right? So those products were going to be at the exact same energy level, no matter if we were dealing with our straight chain C8H18 or our branch CHH18, right? Those products were always going to be, for both of them, 8 CO2 and then 9 H2O. So because the products are the exact same, those products are always going to have that exact same energy level, or that exact same, let's not use energy, but exact same enthalpy level, right? Now, the differences between the products and the reactants were different because overall those enthalpies, those heats of combustions were different. So when we looked at our straight chain octane, right, if we looked at the energy level of them, we can measure that by the difference in the enthalpy, right? So the enthalpy here was a minus 5,472, 5,000, not 472, 470, right? Comparing that, knowing again that the products are the exact same energy level to our branched octane, because this difference or this delta H was smaller, right? It was slightly smaller. It was minus 5,452 kilojoules. That tells us, since again the products are the exact same, that these guys lie at a little bit smaller less of an energy level than our straight chain octane, right? Because again, we're measuring differences here. If the products are the exact same and the difference between this guy and this guy is less than this one, then that tells us that this is at a little bit lower of an energy state. And that tells us a little bit about its stability, right? So this is at a lower potential energy state, then this means that this guy overall is more stable comparatively to our straight chain constitutional isomer, okay? So again, long term, the big takeaway from this is that when you're comparing constitutional isomers, the more branching, the more substituents, the more branching that you have in the isomer, the more stable it actually is. The less stable molecule is going to be the straight chain isomer comparatively to any type of branching that you're going to get. So if you have branching versus straight chain, the more stable isomer is the branched isomer. Okay, so we're going to move into kind of like a new-ish topic with respect to what we're going to learn in this chapter. And again, it's still dealing overall with this idea behind energetics and stability of alkanes, okay? Coming away from this chapter, this material that we're going to learn here is probably going to be one of the more important things that you're going to learn. We're going to utilize Newman Projections, which is what we're going to talk about quite a bit as we move through the remainder of the course. So it's important that you guys understand what we're dealing with here and how to actually visualize these alkanes and then be able to project or draw these Newman projections from them. Okay, so also things to note, we are going to be dealing with, again, with energetics, with stability. But a lot of what we're going to be dealing with can actually be aided with the help of a molecular model. So at the beginning of the semester, I told you, oh, molecular models are helpful. I'll tell you when it's probably helpful to utilize them. This is that point in time, right? These Newman projections are kind of hard to see when we're dealing with stuff that's on paper. And so if you did have a molecular model, this would be the time to maybe start to utilize it. And I'll try to make a video of drawing Newman projections from models so that you can kind of help see how it would be useful. Okay, so what we're going to deal with here is the fact, number one, we're dealing with alkanes, right? So we've been talking about alkanes. And alkanes, again, are hydrocarbons that mainly the big takeaway is have only single bonds. Okay, so we only have sigma bonds with alkanes. We're only dealing with single bonds. Now, what we also find is that with sigma bonds are allowed free rotation about the bond axis, right? When we talked about the difference between sigma and pi, we talked about how, the sigma bond, you don't break that orbital overlap if you rotate that bond, Whereas with pi bonds, right, where we had that side-on orbital overlap, you do break it if you rotate it, so you can't rotate pi bonds, right? You can't rotate double or triple bonds. You can rotate single bonds, right? And so because we are allowed that free rotation, single bonds do rotate. And what we're going to talk about is kind of the ramifications about those rotations, and the various different what we call conformations that our single bonds or our molecules can take on because those bonds are allowed to freely rotate, okay? Now, a couple issues with this, right? We have been drawing, at this point in time, our bond line structures, right? So when we draw our bond line structures, we know that carbon is represented by all of our little vertices and all of our little endpoints in our bond line structures. And again, when we're dealing with alkanes, the type of carbon that we're dealing with is sp3 hybridized carbon, right? So most important with respect to that, we're dealing with tetrahedral carbon, right? And so when we draw these bond line structures, what we are trying to imply is, again, these carbons are tetrahedral. Anything we draw in the plane of the paper or in the plane of the board is all supposed to be in the same plane, right? And so these guys, these two bonds are essentially implied to be in the exact same plane, meaning that the remainder of the atoms that are attached to that carbon, which again are going to be those implied hydrogens, are not in the same plane. So if you got a tetrahedron right now and you put two bonds in the exact same two-dimensional plane, you would have one thing that is coming out at you, right? And so the way we drew things that are coming out at us was via our wedge, right? So for this carbon right here, if we actually had a model of this guy, we would have a hydrogen that was coming out, pointing out at us, and we would also have another hydrogen that was pointing away from us, right? And so again, we're trying to replicate this tetrahedral structure. Anytime we draw a solid line, that solid line is saying that those guys are in the same plane. So if two of those bonds are in the same plane, then we would have one thing that's coming out at us, which is what we denote via our wedge, and we would have one thing going away from us into the board, which is what we denote via our dash, okay? Okay, so we're taking that, right? We're taking this idea behind bond line structures, and we're trying to assess the various conformations that can happen around these various bonds, because again, we're going to be allowed free rotation, and so that's what we're moving into. That's kind of the entire purpose of this next section. Now, the way we draw it with respect to bond line structures is kind of hard to visualize, right? These various different rotations or these various different conformations, okay? And so because of that, we actually utilize a new way to draw things to help us visualize these different conformations that are available, right? So what we're going to do is we're going to take our wedge dash bond line structure, and one thing that we can do with it is we can draw what is called a Sawhorse projection. And in the Sawhorse projection, we've taken this bond line structure and we've rotated it 45 degrees, right? So we're taking this guy and we're essentially rotating it, and we're imagining what it would look like after that rotation. And that's what we get in our Sawhorse structure. Again, this guy is our front carbon, is this guy, and this guy is what we're going to call our back carbon back here, okay? Now, these Sawhorse projections are kind of difficult to draw still, right? So there's an easier way that we can draw this to imagine these conformations again. And so what we're going to do is we're going to take our Sawhorse and we're going to again rotate it 45 degrees. So we're going to rotate again, and we're going to be left with what is called our Newman projection, okay? So just as a note, we're going to deal with a lot of different projections, right? And again, these projections are just different ways to visualize our original bond line wedge dash structure. We're just looking at different ways that make it a little bit easier to see what we're talking about comparatively to having to draw this over and over again, okay? So now I'm going to explain how we get this and what this means compared to coming from Sawhorse or coming from wedge dash. Okay, so the way we imagine this is we will take our wedge dash projection, or I should maybe say bond line projection, or we'll take our Sawhorse projection, and we will imagine that we're staring down a specific bond axis. So people always draw these kind of like, imagine eyeballs just floating in the air. But what we're trying to do is imagine what it looks like if we're staring down this carbon-carbon bond axis. Where are the various things around this, okay? Now, the way we draw this is we're going to have two different things. We're going to have what we call our front carbon, all right? So this guy is our front carbon. And the way we represent our front carbon, what we're looking at, or the first carbon that we see as we're staring down this bond axis, is we represent it by this little dot right in the center, okay? So first step in drawing Newman projection, which is what we're trying to do. So Newman projection from a wedge dash or a sawhorse projection is drawing that front carbon. We're just going to illustrate that via a nice little dot, okay? So now, as we continue to look down here, what we're going to do is we're going to draw the bonds away from this front carbon by essentially trying to replicate where they're at, right? So as I look down this bond, this thing, in my vision, essentially looks like it's pointing straight down, right? So this bond is going to be represented coming from my front carbon, pointing straight down. And so that's a hydrogen. I'm going to represent it by whatever it's bound to. This thing, if I can get another color here, this guy, if I was looking at it, again, pointing in the direction of the eyeball, it would appear to me as if it was pointing up and to the right, right? This guy looks to me like it's pointing up and to the right from my front carbon, whereas this guy, this other guy, looks to me like it's pointing up and to the left. So I can also draw that guy over here, up and to the left in my Newman projection, okay? So again, this is this front carbon that we're imagining. We're now going to project and imagine us visualizing this through to this guy, which is what we call our back carbon. And the way that we represent our back carbon in Newman projections is we represent it via a big circle, right? So we have our front carbon represented by that dot. That back carbon is essentially something that we can't really see, but we represent it via a circle, right? So again, as I'm looking down this bond axis, I'm now looking at the things that are attached to this back carbon. And as I'm looking at that, I see that this hydrogen looks like it's pointing directly up, right? So I'm going to go ahead and represent that by drawing a line that's pointing directly up from my back carbon. Then I have, let's say, this guy, again, that as I'm looking down at this, looks like it's pointing off and to the right. So down and to the right. And then I have this guy, as I look through this, that looks like it's pointing down and to the left. Okay, so this is how we're going to get these Newman projections from either Sawhorse projections or our bond line structures. So now if I wanted to draw this in just all one color, again, I would have my front carbon represented by that dot. I have a bond down to hydrogen. I have a bond up to hydrogen. I have a bond up to hydrogen. I'm then going to draw my back carbon via a circle. I have a bond up to hydrogen, I have a bond down to hydrogen, and I have a bond down to hydrogen. Right? So this overall is this Newman projection for this molecule, which is just ethane, looking down this carbon-carbon bond axis. Okay, so it's important to get kind of practice doing this, right? And so I'm going to go through another example that's looking down a bond line structure of a little bit more complex of a molecule, okay? So right now, what they want us to do is they want us to take this bond line structure. So again, this is our bond line structure. And they want us to draw the Newman projection looking down the bond that they've illustrated via this arrow. So if you want to imagine there's an eyeball here, it's kind of creepy. It's looking directly down this bond axis, okay? So they want overall the Newman projection looking down this bond axis, okay? So again, my first step here is looking at the carbon that we're looking down. All right, so right now this guy is a 1, 2, 3, 4 carbon structure, right? Another way that they could say this, if we went ahead and numbered our carbons, we have 1, 2, 3, 4. They could say, oh, draw the Newman projection looking down the C2 to C3 bond axis. That's another way that they could state this, okay? So if I'm looking down this guy, right, I'm going to represent that again in my Newman projection via just a dot in the center, okay? Now, as I look down this guy, this thing, which is in the exact same plane as the bond I'm looking down, appears to be coming straight down. And as a note here, this is not a hydrogen, right? If we terminate in a carbon, then this is a CH3 group. Another way to state that is this is a methyl, right? So we can represent that as we draw this Newman projection as just saying methyl, or you could also have said CH3 as well, right? So those are two exact same things. I'm going to go ahead and write CH3 just so that we make sure that we keep our carbons. So as I look down this, I'm looking down here, I've got a CH3 group. Now, they show us a wedge for the bromine, right? And so that wedge, as we look down this, is coming out at us as we look at it. But if I'm looking down this bond axis, to me, this is to my right and it's up. So I can draw that bromine to the right and up. There is another bond there that's being implied though, because they only show us 3 of them. So there is an implied hydrogen that's actually going into the board at this point in time. Because again, we've got 2 bonds in the same plane. The other bond has to be coming out at us. The other bond has to be going into the board. So that implied hydrogen is going into the board. And as I'm looking down this bond axis, that other hydrogen, it appears to be pointing up into the left. Right, so again, it's hard because like I can't, I'm using my hands to try to imply what I'm looking at, right? But you guys can't see that, so it's hard to necessarily do that. Okay, so again, this is our first step. This is our front carbon. So then the next step is drawing our back carbon. Again, how do we represent our back carbon, right? We represent it via circle, right? So we'll go ahead and draw a circle, right? Looking at this guy. Again, we're looking down this exact same bond axis, right? So if we're looking down this, then this thing appears to be popping up, right? And again, this thing is the exact same thing that we saw over here. This is a CH3 group. So coming from our back carbon, that methyl group is up top, popping directly up. We have this bromine. Let me try to use a highlighter here. We have this bromine that as we look down coming this way appears to be pointing down into the right. So we can draw that with our pen down into the right from that back carbon. And again, there is an implied hydrogen that now as we look down this guy is pointing down into the left. Okay, so this is the Newman projection for this molecule looking down the C2 to C3 bond axis, right? This was carbon 2, this is carbon 3, this is the bond we're looking down, and this is what we would see if we were actually pictured here. Maybe I should draw a human, like a stick figure. So if we were actually here and we were looking down this bond directly, this is what we would see, or this is the visualization of what we would see. We'd see a methyl group on that front carbon pointing down, a bromine on that front carbon pointing up and to the right, a hydrogen pointing up and to the left. We would look through that, we'd see that methyl group pointing up, we'd see that bromine pointing down into the right, and that hydrogen pointing down into the left. Okay, so go ahead and try this one out. So I've drawn 3 different molecules, and I have shown you what bond axis I want you to look down, and I want you to draw the Newman projection looking down those bond axes, right? So here we're looking down this bond, this carbon-carbon bond. I want you to draw the Newman projection. Here we're looking down this bond. I want you to draw the Newman projection. And here we're looking down this bond. I would like the Newman projection from that. Okay, so get some practice with this, give this a try, maybe do the first one. So we'll start with this guy, see how you do, and then maybe pause it and move on to the next 2. Again, that I would go ahead and push pause, work on this, and then come back for the answers. Okay, so I'm going to start with this molecule to the left over here. We'll call this, I hate when I do that. We'll call this molecule A. Again, we have, let's say, 1, 2, 3, 4 carbons here. And so we're looking down. If we go 1, 2, 3, 4. For this bond, we want the Newman projection looking down the C2 to C3 bond axis. So again, if I do this, first thing I'm going to do is I'm going to start with my front carbon. We have our front carbon here, right? And again, we're going to represent that via just a nice little dot. So we don't draw the 3D perspective here, but we can imagine that this guy is on our wedge coming out at us, and then we can imagine that this guy is on our dash going into the board. So now I'm going to focus first on what this guy is down here, this bond that's pointing down. So again, this is a carbon. It is a methyl group, right? So there's a C3 group or CH3 group. Same thing here, we've got a carbon methyl group, and here we've got a carbon methyl group, right? So if I drew this in my Newman projection, the thing that's coming down is this guy. So this guy is coming down, and I'll go ahead and say CH3. The thing that is pointing up and to the right is this guy, and I'll draw that as CH3. And then the thing that is pointing up and to the left is this guy, and I'll go ahead and draw that as a CH3. Okay, so that is my front carbon. We're now going to look down this at my back carbon. And for my back carbon, I only have one thing that's drawn that's attached to it, right? So we know that the other two things for that bond, because again, we're dealing with tetrahedral carbon, is a hydrogen. It has to be coming out at us. And then we also have a hydrogen that has to be going into the board. Those two things are implied. Okay, so now, as I look back down, if I was looking here through this bond, the only thing I would see is this guy sticking up, right? So I'm going to go ahead and draw my back carbon as a circle. I see this methyl group sticking up. So this guy is CH3. It's attached to my back carbon. And then the other two things I would see is a hydrogen here that's pointing down into the right. So I draw that as a hydrogen. And then I have a hydrogen here pointing down into the left. Right, so, oh, pardon me, this is a CH3. So this is the Newman projection looking down this bond axis. We've got our front carbon, and then we've got our back carbon, Okay, so hopefully you guys did well on that one. Go ahead and try what we'll call B here, and then come back for the answer. Okay, so again, if we were numbering this, we'd have 1, 2, 3, 4, 5, 6. So this question, they want us to draw the Newman projection looking down the C3 to C4 bond axis. And again, maybe some of you are wondering, why did I start numbering 1 over here at this position as opposed to over here? And again, remember, when we number, we want to give the first substituent the lowest number possible. If I had started numbering over here, that would have given 1, 2, 3, 4. 3 is lower than 4, so we're going to start numbering over here. That's why I started numbering on the right instead of the left. Okay, so again, first thing first, we're going to draw our front carbon. Front carbon is carbon 3. We have this dash going into the board. That dash is again representing a CH3 group. We have bond here. We have bond here. These guys are in the same plane. And so just as a reminder, that means that there is an implied hydrogen that has to be coming out at us. Okay, that's important to know when we're actually trying to draw the Newman projection. Okay, so first things first, we have our front carbon. If I look down at this guy, then the first thing I see is this same thing, or this bond that's in the same plane as the bond we're looking down, that appears to be pointing down. The only thing to note here is that this thing is a CH2CH3 group. So there are a couple different ways that we can represent that. If it's a 2-carbon chain, like I've just said, we could say that that is an ethyl group, and we could represent it as ethyl or ET. We could also just give the molecular formula for it. So this is a CH2CH3 group. But again, it's everything that's coming down here, right? So it's this bond with everything attached to it. So I'll go ahead and write CH2 CH3. And again, I could have said ethyl, I could have said ET to represent ethyl as well. Okay, so now I'm looking what's pointing up and to the right. So the thing that's pointing up and to the right is this guy, which is a hydrogen. So I'll go ahead and draw that on my Newman projection. This is a hydrogen. And then the thing that's pointing up and to the left is this guy. So I'll go ahead and write that on my Newman projection. This guy is a methyl group. Again, I could say CH3. I could also represent that as methyl. I could also represent that as Me. That's another way that we represent these guys. Okay, so that is all of my front carbon. Now I'm going to look down to my back carbon. The only thing I see drawn is this bond to these guys, right? So we have this bond here that's pointing up. Again, there has to be 4 bonds to carbon here, so we know that there's an applied hydrogen coming out at us, and there's an applied hydrogen going into the board. Let me draw that a little bit better. Make it visually more appealing. So this guy's coming out, this guy is going in. Now, as I look down my back carbon, I'll go ahead and draw it as my circle. The thing that I see pointing up is this guy, and again, this is a CH2CH3 group. So I'll go ahead and represent that CH2CH3. Now, as I look down this bond again, I see the hydrogen pointing, let me turn. I see the hydrogen looking down to the right, or looking down this bond. I see the hydrogen that's pointing down and to the right as this guy, right? So again, I try to situate myself so I can kind of visualize this. If anything is pointing into the board, coming from here, then that's going to be down and to the right for me. So this guy, pardon me. This guy is this guy. And then here we have anything pointing down and to the left, it would be coming out. So this guy is this guy. So note that there's a separation here. This was a methyl group and this was an ethyl group. Again, another way to have drawn this would have been hydrogen, ethyl, methyl with a circle, and then ethyl, hydrogen, hydrogen. Okay, so then finally we'll go with number C, or letter C. I like how I just completely erase all my conventions. I just forget them all. Okay, so for this guy, we've got carbon, 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 carbon. We're looking down the C2 to C3 bond axis. And we're wanting to draw the Newman projection from there, okay? So go ahead, give this a try, pause the video, and then come back for the answer. Okay, so again, we draw some weird eyeball. We're looking down this bond. We're going to draw our front carbon first. On our front carbon, we've got a bromine that's coming out at us. I don't know why I try to overdo that. Again, we've got another bond to a carbon up here. Again, this is a methyl group. And the thing that is implied is on the dash going into the board. This is a hydrogen. This is for our C2 carbon. For C3, we've got a dash with a chlorine that's going in. We've got a bond to another carbon that's in the same plane. And so then we know that there's an implied bond coming out at us, which is a hydrogen. Okay, so I'm going to draw my front carbon first. So we have our front carbon. As we look down this thing is pointing directly up. So this guy is pointing directly up. Again, this is a methyl, so we can represent that as not an E, a CH3 or an Me, or you could write out methyl. As we look down this, right, that bromine that's coming out at us, if I rotated my body to look down this, that bromine is pointing down and to the right. And that means that the hydrogen is also pointing down, but it's going into the board, which is to our left at this point in time. Okay, so that is front carbon. We'll do back carbon. So now as we look down this at our back carbon, the thing that's pointing down is again that CH3, that methyl group. So this is a CH3 group. Now as I come out, this thing that's coming out at us, if I turn my body, it's actually pointing up and to the right. So that hydrogen is pointing up and to the right. And then this chlorine, which is going into the board, again, as I rotate my body, is pointing up and to the left. So it's kind of ugly as I draw it like that. If I go ahead and redraw it using our little ethyl convention, I've got a Me, I've got a Br, and I've got an H, and then I've also got an Me, I've got an H, and I've got a chlorine. So a couple different ways to draw the exact same projection. Okay, so give this a shot because it's difficult. Again, hopefully, if this is not making sense, I may make a video with some more spatial awareness to kind of get you guys in the mindset of how I look at this. But go ahead and give these guys a shot, and then email me if you have questions with respect to that. Okay, so we're going to move on. Hopefully you guys have conquered Newman Projections. And we're going to talk about kind of some of the application behind where we're going to be utilizing these Newman Projections, right? So I've talked already about how these alkane molecules can undergo different conformations. And I'm going to try to explicitly, I don't know what I'm doing here. Try to explain exactly what I mean by these different conformations, okay? All right, so we're going to go back and we're going to kind of introduce this topic utilizing ethane as an example, right? So ethane, we drew the Newman projection for originally. We had a carbon that was bound to another carbon, right? So it's just, ethane is just two carbons. Again, both of them are going to have hydrogens attached, right? So we can go ahead and draw one of those hydrogens in the plane of the board. We can draw one of them coming out at us, and we can draw one of them going in. And on the other hydrogen, we can do the exact same thing. One of them's in the plane, one of them's coming out, and then one of them's going in, right? And so this is, again, wedge dash projection or drawing of ethane. And then we got the Newman projection from that, okay? Now, when we talk about different conformations, this goes back to the fact that this bond can rotate, right? And so if this bond rotates, then our Newman projection, or the position of this hydrogen relative to this hydrogen and vice versa is going to change, right? So the way that we have drawn it at this point in time is in what we call the staggered conformation, right? So in the staggered conformation, we've got everyone staggered relative to one another. And in this conformation, something that we're going to be very interested in is something called this dihedral angle or this torsional angle. And what this is essentially measuring is this angle between this guy and this guy, right? And again, we can see that a little bit better in the Newman projection. We're looking at where this guy is, so where this hydrogen is relative to this, okay? In the staggered conformation, these guys are kind of maximally spaced out. This ends up being about 60 degrees with respect to one another, okay? Now again though, we can rotate this bond. So if we start to rotate this bond, that angle is going to change, right? So if we start to rotate, let's say this guy going this way into the board, then this guy's going to start getting closer and closer and closer to this hydrogen. This guy's going to start to get closer and closer and closer to this hydrogen, and this guy will do the exact same, right? So this torsional angle, torsional or dihedral angle can change depending on the rotation of that carbon-carbon bond, okay? Now, this different dihedral or torsional angle, this is what we mean by different conformations, right? Because this can change, because we can rotate, we're going to get different conformations with respect to the exact same molecule, okay? Now, there are going to be two conformations that we're really interested in talking about or learning more about. The first one we've already introduced, which is the staggered conformation. Again, when we have a dihedral angle of 60 degrees, these guys are completely staggered with respect to one another. And another one is something called the eclipsed, okay? Okay, so again, we have our staggered conformation. And if we drew the Newman projection, or the bond line structure for this, we would end up with something, again, that looked like this, right? Where these guys are completely staggered with respect to one another. The other projection, or the other conformation that we are interested in, is something called the Eclipsed Conformation. And what happens here is essentially, if we draw the bond line structure for this, we've got everything essentially eclipsing one another, right? So just like I forget, is it the moon that eclipses, it completely covers it, right? Goes over it. That's why we call these guys these eclipsing conformations, right? So if we drew the bond line structure for an eclipsing conformation, it would look something like this, where this guy completely eclipses this guy completely eclipses this guy, and this guy completely eclipses this guy, right? For the eclipse conformation, this dihedral angle is essentially 0 degrees, right? They are essentially right on top of one another, okay? Now, again, two conformations we're super interested in, staggered and then eclipsed. Okay, so also something that's important to note, and we're going to explain why here in a second, is the fact that this staggered conformation is actually the more stable conformation. It is lower energetically in energy, and the eclipse conformation is actually the highest in energy. It is the most unstable conformation overall. Okay, so energetically, much more favorable to be in the staggered conformation versus the eclipsed. Okay, now the question is why, right? Why would this be better or more favorable to be in the staggered conformation? So we're going to go ahead and explain that in a second, but instead right now we're going to look at the difference in energy between these two conformations, between our staggered and our eclipsed. Okay, we're going to explain. So we can create what is called kind of an energy diagram, right? And so what we're looking at here is energy, and this is as a function of this dihedral angle, right? So we're taking ethane, essentially, so I'm going to go ahead and draw it. And what we're going to start out with, over here on the left, is this dihedral angle of 180 degrees. And what we're comparing here is not necessarily one hydrogen next to another hydrogen, but what we're comparing is, or what we're starting with here, is this hydrogen relative to this hydrogen, right? So right now, these guys are here. They're 180 degrees away from one another, okay? Now, what we're going to do is we're going to change that dihedral angle, and we're going to do that by rotating this front carbon, right? So we're going to take this front carbon, and we're going to rotate it to the right, right? And so, let me go ahead and draw in. I've ignored two hydrogens here. We're going to rotate this to the right, okay? So we start here. We're going to pull this guy to the right, and what we're going to find is we're going to initially move in from a staggered conformation. As we rotate this front carbon, we're going to move into this eclipsing conformation, right? And again, what we see is this increase in potential energy as we move from the staggered, which is the most stable conformation, into the eclipse conformation. We can continue to rotate this guy, right? So we're continuing to rotate that front carbon. We will move back into that completely staggered conformation. And as we continue to rotate, we will again now have another eclipsing conformation. As we continue to rotate, we move back into the staggered. As we continue to rotate, we move back into an eclipse, okay? So as we take this guy relative to this guy and we rotate him throughout the entire molecule, what we find is we have 3 different eclipsing conformations. So this is 3 different eclipse. This is great. Eclipsing conformations. And then we also have 3 different staggered conformations. So 1, 2, and 3. And this guy actually just gets us back to number 1. Right? So 3 eclipsing conformations and 3 staggered conformations. Okay? And so we can also measure the difference in energy between the eclipse and the staggered. And we find that this ends up being about 12 kilojoules per mole. Another thing to note is that all of these staggered conformations have the exact same energy level. There's no difference between this staggered conformation and this staggered conformation. So anything that has same energy is what we call degenerate. So this is same energy. So we call this a degenerate conformation. A degenerate. Same thing for the eclipsing conformation up here. All of these guys have the same energy, so they are also all degenerate. They're all equal in energy, okay? There's no difference between one eclipsing conformation versus another. There's no difference between one staggered conformation versus another, okay? Okay, so again, difference in energy here is about 12 kilojoules per mole. Now, because of that, the movement from the staggered to the eclipse costs us 12 kilojoules per mole, we can kind of get an estimate on how much each eclipsing interaction costs us, right? So again, if this total cost between staggered and eclipse is 12 kilojoules per mole, in the eclipse confirmation, we get 3 different hydrogen-hydrogen eclipses, right? So we can kind of estimate that each hydrogen-hydrogen eclipse costs us about 4 kilojoules per mole. Because there are 3 of them, that's why we see this total cost of 12 kilojoules per mole. Okay, so then also one last thing to note, why, right? Why is there a difference between the staggered and the eclipse confirmation? Why is there this energy difference? So one way that we can look at this is via what's called steric interaction, right? So again, if I draw out a very ugly bond line structure for this ethane molecule, right? So we've got hydrogen, 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 right? And then we move this, let's say, into an eclipsing conformation. So we've got a nice eclipsing conformation. We have to think that these bonds, right, have this electron density in them. And as we move into this eclipsing type conformation, right, we've got electron density here, electron density here. There's going to be slight steric interaction here. So steric interaction, at least this is how it was explained to me when I was in college. So because of that steric repulsion, that's what essentially costs, or that's why the eclipsing conformation is higher in energy. You don't get that same exact amount of steric interaction or steric repulsion in the staggered, right? And so that's why it's a little bit lower in energy. The actual current reason why there's a difference in energy here is not necessarily due to something unfavorable in the eclipse. I need to learn how to spell again. I haven't spelled eclipse in a while, so eclipse. It's not that there's something energetically unfavorable in the eclipse. It's actually the fact that in the staggered confirmation, there's something energetically favorable that happens there, and that's why it's actually at a lower energy state. So the current explanation behind why there's a difference here is the fact that in the staggered confirmation, what we get is orbital overlap between a bonding molecular orbital on one carbon and an anti-bonding molecular orbital on another. And that orbital overlap allows for there to be this like spread out again of electron density, right? And so anytime we get a spread out electron density between more than one atom or more than one center, that tends to be energetically favorable. And so the current rationale of why the staggered is energetically more favorable than the eclipse is because we get a spread out electron density in the staggered between these two interactions, or between these two molecular orbitals. We don't get that in the eclipse. That orbital overlap breaks when we move into the eclipse, and that's why it's at a higher energy. Regardless, long-term, a hydrogen-hydrogen eclipse is going to cost us about 4 kilojoules per mole in energy anytime we move into that eclipsing conformation. And we call this, or this difference between these guys, we call this torsional strain, right? Yeah, so this difference in energy between the staggered and the eclipse for ethane, we call this torsional strain again, like I just said. And again, one more time, just for everyone in the back of the room who may not have heard me, each of these hydrogen-hydrogen eclipsing interactions is going to cost us 4 kilojoules per mole, okay? Okay, so, great. That's right. Awesome. That's ethane, right? Now, we have to talk about a different molecule, right? We have to talk about propane, let's say, okay? So, I'm going to go ahead and draw out the bond line structure of propane. 3 carbons, nice and easy. We're going to look at the Newman projection and the different conformations for propane, looking down this bond axis, right? So again, we've got our nice implied hydrogens. We've got a hydrogen coming out. We've got a hydrogen going in. And let's say that we start in our staggered conformation. So we're going to have a hydrogen on this back carbon. We're going to have a hydrogen, and we're going to have a hydrogen, okay? So now if I draw the Newman projection for this guy, looking down this bond axis, I've got my front carbon pointing directly up is going to be a methyl group, and for whatever reason, I keep trying to do that. pointing down and to the right is going to be a hydrogen, and then pointing down and to the left is another hydrogen. As I look towards that back carbon, I've got a hydrogen pointing down, I've got a hydrogen pointing up to the right, and a hydrogen pointing up to the left. Okay, so we're going to start here. We're going to look at the different dihedral angles, different conformations that we're going to find for propane. Okay, now if we start where we are, what we just drew, right, what we're going to do is we're going to take this front carbon and we're going to rotate it this way, right? So we're going to take this front carbon and we're going to rotate it. Again, we start in a staggered conformation, which we know is energetically favorable, lower in energy. We're going to rotate this guy to the right, and we're moved directly in to our first eclipsing conformation, right? So we get to this higher potential energy state. Again, as we continue to move this guy to the right, we're going to move back into the staggered. As we continue, we'll move back into the eclipse. As we continue, we move back into the staggered, we move back into the eclipse until we get back to where we originally started from, okay? Okay, so again, a couple of things to note. This dihedral angle that we're measuring is between this guy and this guy. It starts at 180 degrees and moves all the way to 60. It moves to 60, it moves back to 180. Also, things to note. All of these eclipsing conformations are all equal in energy again. Equal in energy. None of them have any differences in energy, so these guys again are all degenerate. Same exact thing for all of our staggered conformations. All the staggered conformations are also equal in energy. They're also degenerate. I don't think I'm spelling staggered right at all. It's ER. I don't know why I think it's AR. These are things that aren't really explained. And I don't even think it's staggered. I'm not even doing the ED at the end. I mean, that's bad. Okay, erase, staggered. I need like a mnemonic to remember that or something. Okay, degenerate, staggered. They're all equal. That's great. What's the point? Who knows? Okay, so one other thing to note about propane, the only big difference here is the fact that in moving from our staggered RED to our eclipsed, we have a difference in energy here of about 14 kilojoules per mole, right? So the difference here, right, when we move into the eclipse, we have a hydrogen-hydrogen eclipse, we have a hydrogen-hydrogen eclipse, and we have a methyl-hydrogen eclipse, right? When we had 3 hydrogen-hydrogen eclipse, that cost us 12 kilojoules, and we estimated that because of that, each hydrogen-hydrogen eclipse cost us about 4 kilojoules, right? So now we have 2 hydrogen-hydrogen eclipses. So if we have 2 times 4, that accounts for 8 kilojoules total of the 14 kilojoules. So now that leftover amount between 14 and 8, which is 6 kilojoules, we can say is essentially due to the methyl hydrogen eclipse that we see in our propane molecule, right? So that tells us that a hydrogen-hydrogen eclipse costs us about 4 kilojoules. Now a methyl hydrogen eclipse is going to cost us about 6 kilojoules, which is a little bit more overall comparatively, okay? Okay, so that is propane, right? All eclipse conformations are equal in energy. All staggered conformations are equal in energy. We have a methyl hydrogen eclipse now costing us about 6 kilojoules per mole. Okay, so now we're going to move on to butane. And this is where we're going to start to see some differences with respect to these energy levels, right? So I'm going to go ahead and I'll draw out the bond line structure of butane. Right, so we'll start 1, 2, 3, 4. So we have butane here. Again, what we're going to be looking at down is the C2 to C3 bond axis, right? So again, we've got a nice little implied hydrogen here, a nice little implied hydrogen here. We've got one up here, and we've got one up here. So if we draw the Newman projection for this, we've got our front carbon. That front carbon has a bond up to a methyl group, so we have a CH3. We have a bond to the left and to the right to the 2 hydrogens. As we look towards that back carbon, we've got that CH3 pointing down, and then up and to the right, a hydrogen and a hydrogen, okay? So we're going to start here and looking at the different energies of the different conformations as we rotate, again, this front carbon to the right here, okay? So if we start down here, both of these methyl groups are at 180 degrees with respect to one another. We're going to take that front carbon, we're going to start to rotate it to the right. And as we do, we move into our first eclipsing conformation, where we get a methyl hydrogen, and a hydrogen-hydrogen. We're going to continue to rotate this guy to the right, and we move into our staggered conformation, right? As we continue to rotate this guy to the right again, we move into another eclipsing conformation. We continue, we move into a staggered, we continue, we move into an eclipse until we get back to that 180 degrees where we started at. Okay, so now there's a couple of things to note that are a little bit different comparatively, right? So again, we have 3 different eclipsing conformations. Now, these guys are not equal in energy, and we're going to talk about that in a second. So here we have an eclipsing conformation that is equal in energy to this eclipsing conformation, but this guy is a little bit higher in energy relative. And then we also have differences in our staggered conformation. So these guys are also not degenerate, they're not equal in energy, right? So we have a lowest energy state when we have this methyl and this methyl 180 degrees away from one another. When we get these guys closer together, so this is a 60-degree dihedral angle, we have a little bit higher of an energy. Again, this is a 60-degree dihedral angle, so these guys have equal energy here. And then as we move them back out, we get them 180 degrees relative. That's going to be at the lowest energy. Okay, so we're going to talk about, first off, the differences between our staggered conformations, and then we'll talk about what we see with respect to the eclipsing conformations. All right, so we had 2 different types of staggered conformations. One where these guys were 180 degrees apart from one another, and then the other where they were 60 degrees apart from one another, right? So those 2 guys are given 2 different names. So when we have these groups as far away from one another as possible, this 180 degree dihedral angle, we call that the anti-conformation. And again, this is going to be our lowest energy conformation. When these guys were 60 degrees apart from one another, this is something that we call the gauche conformation. So it's gauche. Gauche is, I forget what it actually means in French, but it's French, so that's why it's called gauche, even though it looks like it's gauche. Maybe it's gauche. I think it's gauche. Anyways, so this again, 60 degrees. This is still a staggered conformation, but it's going to be at a little bit higher energy, and that energy level was actually 3.8 kilojoules per mole higher than the anti-conformation, right? And there were 2 different gauche conformations. Again, it's when these guys are right next to each other, okay? So now the question is, well, how can we explain why this is a little bit higher energy than this guy? And this is where we really actually invoke that idea behind electron repulsion and steric interaction, right? So if you guys actually drew, or if you put together a model where you actually saw the actual like closeness of these 2 methyl groups on the 2 different carbons, right? So if you made a molecular model of butane and you rotated about that C2 to C3 bond, you would see that these guys in the gauche position, when they're 60 degrees relative to one another, they actually do start to interact quite a bit because they're very large. They're very, what we call, bulky in terms of electron clouds and electron repulsion. And so because you do start to see these guys interacting, that's what's going to essentially increase that potential energy, right? When they're really far apart from one another, you're not going to get that electron repulsion or that steric interaction. But when they're in this gauche position, that's when you do get them kind of interacting with one another and being repulsed by one another. And so that's why we do have a little bit higher of an energy in the gauche position versus the anti. Okay, so again, big idea, big takeaway here. The anti position, where this dihedral angle is 180 degrees, that's going to be the lowest energy conformation for any molecule that we're going to deal with, right? Again, we have 2 other staggered conformations that are still lower in energy than the eclipse, but those guys are going to be a little bit higher in energy relative to the anti. Okay, so these two gauche interactions, we have a dihedral angle here, looking at the two methyls of 60 degrees. There are two of them. They are degenerate with respect to one another, but they're going to be a little bit higher in energy with respect to the anti position, right? Anti is going to be lowest energy state. Okay, so now we're going to go back and look at those eclipsing conformations of butane. And to do that, I'm going to go ahead and redraw the eclipsing conformations. So we just talked about the staggered conformations. We had one staggered conformation for butane that had the methyl groups that were anti. That was the lowest energy conformation. And then we had two different conformations that had those methyl groups gauche. And those were a little bit higher in energy, but again, they were lower in energy than the eclipsing conformations, okay? We saw the same thing with the eclipsing conformations. We had two of them that were degenerate, that were equal in energy, and then one of them that was a little bit higher in energy, right? So I'm just going to redraw those really quickly. The first one, what do we have? We had back carbon, and the back carbon was a hydrogen, and then a methyl. And then that front carbon in that first eclipsing conformation, we had the methyl here, we had a hydrogen, and we had a hydrogen, right? So then if we keep rotating, if I just keep doing that back carbon steady, and that's what essentially you're going to do for all of these, is you're going to keep one of the carbons steady and you're going to rotate the other one. This moved the methyl here. If we take this guy and rotate it 60 degrees, it moved a hydrogen here, and moved a hydrogen here. And if we do that one more time, we have a hydrogen. Again, that carbon is constant. Keep it steady. Now we've got the methyl here, we've got the hydrogen here, and we've got the hydrogen here. All right, so what I've done here is I've taken this front carbon and I've just rotated it 60 degrees. I've rotated it again 60 degrees to get these various conformations, okay? Okay, so for this first one, we can actually calculate it based on the stuff that we already know, right? So we had already calculated what a hydrogen-hydrogen eclipse cost us, and we'd also calculated what a hydrogen-methyl eclipse had costed us, right? So for hydrogen-hydrogen, we calculated that to be 4 kilojoules per mole. And then for methyl hydrogen, so CH3 hydrogen, we also calculated that. For this guy, we've got two of them. Each one was 6 kilojoules, so 2 times 6, not 16. 2 times 6 is 12 kilojoules. So then adding those guys together for this conformation, for this eclipsing conformation, this is total 16 kilojoules per mole. So what we find is the same exact thing over here. This guy is degenerate with respect to that first one. We get a hydrogen-hydrogen eclipse, and then we get two methyl hydrogen eclipse. So this guy is also going to be 16 kilojoules per mole, right? Now, this guy in the middle, this is going to end up being our highest energy conformation. So what we find here is we find in this guy we have a hydrogen-hydrogen eclipse. We've got a hydrogen-hydrogen eclipse, but for the first time we have what is a methyl-methyl eclipse, okay? And so total, this guy ends up being 19 kilojoules. So this guy ends up being 19 kilojoules per mole. Again, the total is 19. We know what hydrogen-hydrogen costs, so we have 2 times, these guys each cost 4, so 2 times 4 equals 8. So to calculate what this methyl-methyl costs, we're going to take 19, we're going to subtract the 8, and we end up with an 11 kilojoule per mole penalty for having those methyl groups eclipse one another, okay? Okay, so now we've calculated quite a bit of these eclipsing interactions as well as these staggered interactions, and so we can kind of summarize that on the following slide or the following table, right? So we now know what it costs to have a hydrogen-hydrogen eclipse. We know that costs about 4 kilojoules per mole. We know what a methyl-hydrogen eclipse costs. It's about 6. We know a methyl-methyl, it's 11. And overall, with respect to all of these various conformations, the larger the alkane that we're eclipsing, the larger the energy penalty. So the greater the energy it's going to cost to actually have that move into an eclipsing conformation. So larger energy penalty. So we stop like calculating these here unless I give you actual values. But just note that, like, so we have a methyl. We know that this costs 11 kilojoules, and we can abbreviate that methyl. If instead I was dealing with, let's say, an ethyl-methyl eclipse, right? Then because I know that methyl is 11, I know that this guy is going to be larger, even though I don't necessarily have a number, right? So we could estimate it, let's say maybe it's like 14 kilojoules per mole or something. But the larger these guys are, the larger the energy penalty. So if I had a propyl methyl eclipse, that would be larger as well, right? So again, the larger these various alkanes are that we're eclipsing, the larger the energy penalty. That's also similar for our staggered conformations, right? So we saw that when we had our two methyl groups in the gauche position, so 60 degrees apart in our staggered conformation, that cost us 3.8 kilojoules. If instead we had, let's say, an ethyl group and a methyl group that were gauche, then this would be larger in energy, or a larger energy penalty than just the methyl. Right, so this would be larger. Same thing if it was propyl methyl or propyl ethyl. The larger these guys are, the larger the energy penalty for putting them in these unfavorable conformations. Okay, so this is a lot, right? I totally get that, and this is going to be a pretty long PowerPoint or pretty long presentation. But I'm going to go ahead and move into like kind of what we're going to use this for to give you guys some examples, and then we'll move on. So a lot of times what we're going to be doing here is we're going to give you a molecule, and we're going to have you calculate both the lowest and the highest energy conformation for that molecule, okay? So for example, I've given you a molecule here. This is 1, 2, 3, 4, 5, 6 hexane. So 3-methylhexane. We can go ahead and write that out. 3-methylhexane. And what they want you to do is looking down the C3 to C4 bond axis, they want you to identify the lowest energy conformation and the highest energy conformation. Okay, so lowest energy and highest energy. Okay, again, regardless of what we're looking at, anytime we're asking for the lowest energy conformation, we're looking for the staggered conformation that is lowest in energy. Anytime we're looking at the highest energy conformation, this is only ever going to come from one of the eclipsing conformations. So we have eclipsing conformations, okay? Now I'm going to go through how you would solve this, or how I solve this, and then I'm going to let you guys do some on your own, okay? So first step, they want to look down the C3, C4 bond axis to find these conformations. So my first step is going to be, number one, to identify that bond axis. So we've got 1, 2, 3, 4, 5, 6. They want us to look down C3 to C4. And then my second step in doing this is to draw the Newman projection for this so that I can see these various conformations, okay? So if I am doing that, I've got my front carbon. I'm going to go ahead and draw this guy. We'll do it below because that just makes more sense. So I've got my front carbon, and I'm going to draw it as is drawn in this bond line structure. If I look at this, I have a methyl group, and again, I kind of rotate my body to look down whatever bond axis I need. I've got a methyl group that's pointing out of the board, all right? So for me, that's pointing down and to the right. There is an implied hydrogen that we can draw on the dash here. That's going to be pointing down and to the left. And then pointing up here is this 2-carbon chain, right? So we have pointing up an ethyl group. So I'm going to abbreviate that as an ET. You can also say CH2, CH3, or you could write out ethyl. Again, I just said pointing down and to the right was this 1-carbon chain, which is a methyl group, and then pointing down and to the left is a hydrogen. Okay, so again, I'm looking through this bond, looking at my back carbon now, and I'm going to represent that via my circle. We have 2 implied hydrogens here. One of them is coming out at us. One of them is going into the board. And then this thing is another 2 carbon chain. So I'll go ahead and draw the ethyl group pointing down. We've got a hydrogen pointing up to the right and a hydrogen pointing up to the left. Okay, so again, this is A. We already have drawn this in our staggered conformation. That's kind of what it comes to us as, okay? So now, to see the various staggered conformations, what I'm going to do is I'm going to keep my front carbon. So this is what I always do. I keep my front carbon steady. I don't move it. And I'm going to rotate my back carbon 60 degrees, okay? So I'm going to take this back carbon, I'm going to rotate it 60 degrees, and I'm going to draw the new Newman projection that results as that, from that, pardon me. So I've got, again, front carbon steady, it doesn't move. So ethyl, methyl, hydrogen. Now that back carbon, that ethyl group is going to move into this position. The hydrogen is going to move over here, and the hydrogen is going to move over here. And then I'm going to do that exact same thing. I'm going to rotate it another 60 degrees. So we get our front carbon again. This is ethyl, this is methyl, this is hydrogen. And now we've got the ethyl group over here, the hydrogen over here, and the hydrogen over here for that back carbon. Okay? Now, these are all of them. If I rotate that again, I would just be left with what we already originally had. So these are our 3 different staggered conformations. I'm now going to see what type of penalties these various interactions or these various gauche interactions are going to cost us, okay? So in the first guy over here, I'm looking for either ethyl methyl gauche or ethyl ethyl gauche, right? I'm not concerned with hydrogen interactions or hydrogen ethyl, hydrogen methyl. So because of that, the only gauche interaction that we get here is this ethyl methyl. They are 60 degrees apart from one another, right? The ethyl and the ethyl are not in the gauche position. They are actually in the anti-position in this conformation. So the only thing that's going to cost us anything is this gauche interaction. And I'll go ahead and list that down below. We have an ethyl methyl gauche. Okay, so that's the only gauche interaction that we're concerned with. Again, we don't care about ethyl hydrogens or hydrogen hydrogens. Those aren't going to cost us any energy. So now we'll call this guy number 1. We'll move to number 2. Here, we have a couple different interactions, or one interaction. So again, we don't care about hydrogen, we don't care about these guys. The only thing we care about is this ethyl ethyl gauche, right? They're 60 degrees away from one another. So for this guy, we have an ethyl ethyl gauche. That's going to cost us energy. And then on the last one, we've got a couple of different ones, right? We've got actually an ethyl ethyl gauche here. So this guy is an ethyl ethyl gauche, but we also have another one that is this methyl and this ethyl here. So we also have an ethyl methyl gauche. So if we listed that down here, the 2 things that are going to cost us energy are ethyl ethyl, and we also have an ethyl methyl. And both of these are gauche interactions, right? So now, what we're looking for is the lowest energy conformation, right? And again, any of these gauche interactions are going to cost us energy. They're going to increase the energy. So they're all going to be higher the more that they are, right? So because of that, this guy, our last one, number 3, it has 2 gauche interactions. This is like the highest, we'll say this is the highest of the staggered, right? Highest energy, I guess, highest energy of the staggered conformations. Then the other 2, we have a methyl ethyl and an ethyl ethyl. And so you're like, oh, well, I don't know. You didn't give us any numbers for ethyl ethyl. But again, long term, the longer the chain that you're putting into these gauche interactions, the larger the energy penalty, right? So because of that, this guy is actually going to be a little bit greater, the ethyl ethyl, than the ethyl methyl, because both of these have ethyl chains. They're longer hydrocarbon chains. This guy is a little bit smaller, so because of that, this is going to be the lowest energy conformation, and this will be the medium the middle energy. This would be the highest, the third one. So if I had you rank them in terms of, let's say, increasing energy, you would rank them as number 1 as the lowest, which is a little bit less than number 2, which is a little bit less than number 3. And again, number 3 is bad because you have 2 gauche interactions. Number 2 is a little bit worse because you have an ethyl-ethyl, whereas a methyl-ethyl is going to be a little bit lower. Okay, so finally we'll move into B. So B, we're looking at the highest energy conformation. And when we're looking at the highest energy conformation, all we care about is the eclipsing conformations. So I'm just going to rotate. I'm going to take this guy and I'm going to rotate it to find the different eclipsing conformations. And again, I'm going to do the same thing I did before, where I keep that front carbon steady and I rotate the back carbon. So ethyl, we've got methyl, and we've got hydrogen. I'm going to draw the back carbon, and so now I'm going to take that back carbon, I'm going to go ahead and rotate it into the first eclipsing conformation. So I'm going to have my ethyl right by my hydrogen. Now I'm going to have my hydrogen, this guy, right by my ethyl, and then I'm going to have my hydrogen right by my methyl. So this will be eclipsing conformation number 1. I'm then going to do the same thing. I'm going to rotate this guy, but now I'm going to do it 100, not 100, but 60 degrees. So same thing. I've got ethyl, methyl, hydrogen. I am going to rotate this guy, so now we have a hydrogen over here. We've got our ethyl over here, and we've got another hydrogen over here. And then finally, I'm going to do it one more time to get the third conformation. We have ethyl, methyl, hydrogen. So now the ethyl is here. Now we have the hydrogen here, and we have the hydrogen here. So hydrogen, yeah, okay, looks good. All right, so again, we're going to call this number 1, we'll call this guy number 2, and we'll call this guy number 3, okay? So we can actually kind of calculate some of the, well, not really, but because we never talked about hydrogen ethyl, but again, we're looking for things that are going to cost a lot of energy, right? And so for this guy, we can look at the ones that are the various eclipsing conformations. So here we've got an ethyl methyl, or ethyl hydrogen, pardon me. We've got an ethyl hydrogen, we've got a methyl hydrogen. So we can go ahead and say we have 2 ethyl hydrogen eclipses, and then we've got a methyl hydrogen eclipse. Here we've got a hydrogen hydrogen, we've got a methyl hydrogen, and then we've got an ethyl ethyl. So this is ethyl ethyl, this is methyl hydrogen, and then this is hydrogen hydrogen. And then finally, last one, we've got a hydrogen hydrogen, an ethyl hydrogen, and a methyl ethyl. So this is a ethyl methyl eclipse. We've got an ethyl hydrogen, and we've got a hydrogen hydrogen. Okay, so long story short on this one, the ethyl-ethyl eclipse is probably going to be the largest in energy, just because, again, as we increase those carbon chains, we're going to see an increase in the energy penalty to put them in the eclipsing interaction, right? For these two, they both have a hydrogen-hydrogen, and they both have like an ethyl or methyl hydrogen. Again, this guy was like 4, this guy was like 6. We had a penalty, or we had a calculated value for methyl, which was 11. But again, due to the fact that this guy is going to be larger than this guy is going to likely be our highest energy conformation. Highest energy. And again, with these guys, methyl hydrogen 2 times. This is like maybe 2 times 6. And this is another 6, so this would overall be maybe like 18-ish. Yeah, so if we were going to list these, and we call this guy number 1, we call this guy number 2, we call this guy number 3, in terms of increasing energy, then I would say, oh no, the pencil died. Oh no, did it? So increasing energy, starting from the lowest would likely be number 1, followed by this guy I would say is number 2. Oh no, I mean, yeah, this is middle, but that's number 3. Followed by the highest energy conformation is number 2, and that is explicitly or specifically due to the fact that you do have this ethyl-ethyl eclipse, which comparatively is going to cost more energy than a methyl-ethyl eclipse. So lowest to highest, this guy would be our highest energy conformation, which is what they actually questioned in the problem, right? So if you said, what is the lowest energy conformation? Well, it's a staggered one up here. We want lowest energy being this guy, number 1, which had the ethyl groups in the anti-position. And then for the highest energy conformation, that's going to be an eclipsing conformation. And we went with this guy, number 2, because of the ethyl-ethyl eclipse being probably the highest energy penalty overall. Okay, so I'm going to let you guys go ahead and give these guys an attempt. I'm not going to film this today because I'm kind of out of it with respect to filming organic chemistry. But go ahead and give these guys an attempt. I will upload this and then I will answer these on our next lecture, which will be on Tuesday. So good luck with that. And then make sure to email me if you have any questions, and please do the quiz that I posted with respect to the first lecture. Okay, cool. Thanks. Bye.